Okay, so what we have seen in the last class is we defined the viscosity solutions. Now, and then especially we want to look at the solution of this Hamilton-Jacobi-Wellman equation, and then so what are the assumptions we are taking is the usual Lifschitz assumption for B, and again for the cost, and what we don't assume is actually we don't assume that this is uniformly elliptic. So we just take it as elliptic.
Recently have sent it to this.
And then so we have defined the value function v of x to be the infimum over all controls, or admissible controls of discounted payoff.
Save. No. It's open. This should be opened, is it? Huh?
And now, see what my plan is. So what I want, what I am planning is actually the following. So if I assume that V is continuous, and then I will show that V is a viscosity solution to one. Again, under the same assumption, we do a comparison principle. So that means if U1 and U2 are belongs to C of RD, are viscosity solutions, bounded viscosity solutions. To 1, and then yes.
Can you write down the stochastic differential equation also just
Okay. And again, to recall, so this corresponds to the stochastic optimal control problem.
Where is the perturbation? This is Rosalind Abraham.
With the cost function.
This is expansion. These are the variables, transformation variables I take and plug them in the dimensional equations. So these are going to be.
And what one need to do is actually minimize the cost over all controls.
This is
and then, so another thing is we have seen the last class. So this is what I am going to use, the dynamic programming principle. What is it?
So VT is what? I mean, can you just get back?
What is that?
VT.
Ah.
What is the dynamics itself?
depends.
Yeah, see, it's what. Yeah, so
Which are valued properties?
yeah, I'll write down. See, this is actually going to be all measurable functions defined here, and then it should satisfy some non-anticipative conditions. So what it means is, so when you take S less than T, no, that will come later. First you need that the control should not anticipate the future. So that means Wt minus, suppose you are is the driving noise, so Wt minus Ws should be independent of the sigma field generated by the initial condition, and then the process up to S and the control up to 0.
Oh, yeah, you should.
And then the Brownian motion up to 0. So this is the non-anticipative condition we'll be using. And then, so there are some nice theorems which tells that you can go back and forth into feedback control or admissible controls. So what it means is when you start with an admissible control, you can actually find out a corresponding feedback control which is actually going to give an equivalent the same cost. And then we prove the dynamic programming principle which is given by this.
Where is that paper?
How is any finite stopping time?
Remove it.
And this is what we are going to use in proving this. Yeah, any question here? So because this is the framework we are going to use. Okay, and then so this is under the assumption that any continuous viscosity solution you will be having the uniqueness or comparison principle. And then finally what we will see is actually the following. V is indeed continuous. Actually you can do more, you can show that it is order continuous. And if your alpha is large, then it will be Lifshitz.
This is true without the assumption that sigma is not generated.
No. Yeah.
For any sigma.
Any sigma which is elliptic is true.
So non-degenerate, non-degenerate, right?
No. Is
Can be degenerate. So
only we assume this.
sigma is not equal to 0. Sigma prime is not greater. 0 is
No, no.
This is all you need. Okay. So let's start proving actually the first one. So you start with the value function is a viscosity solution. Okay. So how do we start with? See again one and we have defined the viscosity solution. So only just keep in mind that when you deal with the viscosity solution, you have a minus everywhere. So that we will come back whenever we need. Okay, so use the definition. So that I'm going to use the first definition. So you fix an x naught in RD, and suppose phi is a test function, that phi u minus phi has a. I'm just going to prove the super solution part, and the sub solution will be say local minimum. So it will be the minimum at x naught, and again I will just take this to be 0. And I will tell you what one is going to do. So what one do is the following. See, you cannot. The main problem is, see, if the value function was C2, then one can directly apply Ito's formula. So here the trouble is actually you cannot do that. So you need to what you are going to do is actually you are going to use the Ito's formula not for V, which is not okay. So this is value function is always denoted by V. We cannot use the Ito's formula for V, but you can use it for phi. So what one does is actually, and then use the fact that is a local minimum. So in an epsilon ball, what you have is actually in here V is greater than or equal to V. And then, so what you will be doing is actually you look at this equation and take a control, and then you start at the point from here. What you do is actually you only allow the process to evolve till the boundary. There you have the inequality, and then use the dynamic programming principle here, and then so this tau is actually going to be the first time you are going to hit the boundary, and there you replace it with the test function, and then you use Ito's formula. So that's the trick. You got the point, isn't it? So that's all what one is going to do. So you and then okay. So this is what we are going to do. So you have a ball of radius epsilon, and in this, what we have is actually V is greater than or equal to phi, and then suppose tau is actually the heating time. So what will be the heating time? The first time this, and now what one need is to do that we need some estimate. So what is actually going to be this? Can one estimate this? So this estimate you need, and then so this is where we are actually going to be using the martingale inequality. Okay, and what one can do is actually we will be showing that. So this will be less than or equal to Ct square for some constant, and then once you do that, so this will I will just sketch here, but first I will finish actually the outline of the proof, otherwise you may not get much. So once you do that, if you assume this, then take the dPB. So what you will get, and then exactly apply the idea I told you. So what you are going to get is this, which is infimum over V dot of and then so this will be greater than or equal to okay, not this. So what I will do is actually then and for each delta, don't do it for tau, but do it for this. We need smaller ones. Okay, and so this is not x. Our point is x naught. So it is x naught, which is phi of x naught. So what one get is this. which is less than or equal to 0. So now use Ito's formula here, essentially Ito Dingin. So what you do is actually just to that, you just look at, try to apply the Ito formula here, and then pretend that you can do it for stopping times. So that will give you the Ito Dingin's formula.
So this might go. I didn't introduce Ito formula for the students. So
Ito's formula.
Sorry?
Ito's formula?
Yeah. So
okay,
I can
okay.
do it now if you like, but
No, I can, yeah. Yeah, I will do it.
yeah, okay.
Okay, so if you have, so you just take a nice or keep that. So I will now I will remove the control. So without control, suppose this is an SDE, and suppose you have a function phi is in C2 of RD, and these equations are in RD, and what so Ito's formula tells you it's just the change of variable formula. So suppose you just have a differential equation, and then suppose you have this, then what will be this? So and you have a C1 function. So what will be this? You just look at and dxt by dt is the usual. Suppose you have nice functions, then this is what you get. Okay, so how do you get this? How do you prove this? The proof, one can use the heuristics using the Taylor series. So what one does is, this will be, so this look at as the difference, and then what you will get, the first derivative multiplied by the increment, and then you have 1 by 2 factorial, and then you have the second derivative with the square of the increment. So that we can write it as dxt, and plus etc. See, if your process is nice, is of bounded variation, then this is something like square of the variation. It will be 0. So for the deterministic setup, what you get is actually dxt will be 0. And so you mimic the same thing with the capital XT. What will happen? So what is going to happen is this. So here, see, okay, so here I am taking just the one dimensional case, and then just write down for actually the when it is RD. So this take it as D equal to 1. So what you get is xt dxt plus 1 by 2 factorial Of course, then you may think that there may be some additional terms going to come, then you have actually third order variations and so on. Okay, so but what you see is actually this Brownian motion has finite quadratic variation, isn't it? So this will not be 0. So if you use that dwt, which is dt, isn't it? So this term will not vanish, but here it vanishes because this process is of square variation. So what will happen is actually this will be non-zero, and that square variation is actually critical. So whatever variation which is above that will be 0. So this onwards will become 0. So that's actually the second order term comes. So Ito's formula is now you just see it is the change of variable formula, and since you need to consider since there is a non-zero quadratic variation, you will be having actually the second order term, and then the formula becomes this. What will be that? Now one can write it. So this is dxt Okay, so this is gradient because we are not in one dimension, and then 1 by 2, what you will get is second order term. Yeah, so what essentially you are getting is this. I'll tell you why. And then see there are many components to it. So take this as the I comma j. This is what you will get. And now dxt you can actually replace it with this. And what will be this? This you need to look at.
Sigma star.
Yeah, is messy. So what you need to do look at is I will be this. Look at the ith component here plus here each ith component is going to be sigma ij. And now just look at and see the rule is something like this. See, if you have a process of bounded variation, and if you multiply, and the quadratic cross variation of a process of bounded variation with other term will be 0. If you have to non-bounded variation process, something which is like Brownian motion, then you will get something like Brownian motion, the quadratic variation of something like Brownian motion. And so what will happen is actually when you just multiply them, so what are the things you are going to get? This multiplied by this. So these are of bounded variation terms, and this is not. So what is going to left with is actually just the multiplication of the square of this basically.
You can write on multiplication table for dWd and the dt.
Ah.
So dt is 0, then dw is 0.
Yeah, this is what you will be using. This will be 0, and then see what I am telling is actually this is just heuristics, but the idea behind this is actually about the quadratic variation, and then use this. Then and now I will write the final formula. So this you and then I will collect all the dt terms. So here I got 1, and here what I am going to get is this. So this is my bounded variation part plus so this will be the formula. So and how do you prove this? It's exactly the same way. If you want to prove it rigorously, I told you the Taylor series. So you write down the Taylor series, then use actually the quadratic variation, those formulas, and then you need to actually work a bit harder and get all the estimates and pass through the limit. You will arrive at this formula. Okay, so now, but what I want is actually this. So here, so similar to this, one can have, or here I can use this. So I will just remove this. So now suppose you have two processes, there is a product rule. So what type of, so what do you expect? Suppose you have two processes xt and yt, assume that they are given by these two SDAs. So what one expect? So if it was small xt and small yt, then it will be isn't it? And here what you get is actually because you know that there will be a non-zero quadratic variation sitting there, so you get this is the cross variation. So now, so you can use, so now I will come back to this. So what will be the formula here? So this is one process, it's a function, nice function, and this is the process. So if you use that, and so here x will be e power minus alpha t, which is a bounded variation, so this part will be 0. So what you will get is this. And now use the Ito's formula, what we have seen it here. So what you will get? So what you are going to get is d phi and phi. Now the see, you just see that what is this basically? This is nothing but the generator, isn't it? So if you denote this is plus the other term, where it is the generator of this process. So so you can see that this generator essentially comes through the Ito's formula. Okay, so when you do that, do the same thing here. So what you will get is this will be L phi of xt minus alpha dt plus some term, so which is a martingale term for us, because we are assuming everything to be bounded, all the coefficients for us are bounded. Okay, so now pretend that you replace it with the stopping time. What you will get? Just write in the integral form. So what will be this? So this will be expected value of integral 0 to of L of P xs minus alpha phi x multiplied by e power minus alpha s ds is what it is. And plug in this into this, and then and then say I'm just going to remove this now.
So Ito's formula was for even for the stopping time. No?
Yeah, that's the Ito Dingin. So basically what I'm applying is actually the Ito Dingin's formula. So what one get is this. Okay. So now you can write everything. Minus plus r minus alpha phi of xs ds less than or equal to 0. So now what one need to do is divide by 1 by delta and take delta to 0. So here is what one needs this. So what where one uses this is actually, see this split into two cases. First case is actually when tau is less than or equal to delta, and then you write one as, one can be written as this. This is one. And for this, so when tau is greater than delta, then it will be just delta. Then you can pass to the limit easily. And for here, what will happen is actually you have an estimate. So now your t is delta. So what you have is actually it is something like c delta square, and then you are dividing by delta. Still you have a delta there, and pass to the. So what will happen is actually this term will be of the big order of delta. I mean with the 1 by delta, it will be a big order of delta that will go, and the other term one can pass to the limit. But there is a subtle point here. There is an infimum sitting here, so you need to manage that. So how to manage that is actually just take the selector, which will be v delta, and then look at the corresponding solution, which you call it x delta v delta, and take again argue tightness, and then take one limit point and then pass to the limit. So that is what that has to be done. So I told the points. I am not going to do it here. So what one need is actually make the selection and then use.
So existence of selector is obvious, huh?
Which one?
Existence of selector.
Yeah, this is a finite quantity, isn't it? Okay. Yeah. Yeah. It's not obvious. But one can either one can show that can be shown. Yeah, existence of the selector can be shown, because I think you will get a lower semi-continuity here. Yeah, that is one way. You can show that. One method is actually show that the minimizer exists there, and second method is actually just take an delta optimal control you take.
Like in the deterministic.
So you can so you can actually do one of these methods, but here it is more nicer. Here you get actually the selector, the minimizer exists here. Yeah, that's the point.
Space is, target space is a compact set. Huh?
Which one?
Target space is a compact set. The controls.
Yeah, it is compact. See, because that has there is some work here. So to show that, I don't think that I have time here. So what one can do is actually we can see it's something like what you are going to do is actually we give a weak star topology. So what one does, it's So essentially, see what you take. The V is P of U, and U is compact. So what you do is actually you take a separable. So you take a separable class from there, and then use it, and then take all the elements from here. So you can take get an homomorphism into -1 power infinity. And then what you will be doing is actually
identifying V to be equal to -1 infinity.
Exactly, and then you look at actually the you look at some BT board, something like you look at actually the unit board in L2 of 0 to T.
Here the weak could be.
Yes, you need weak star topology.
Weak star topology.
So what you do is actually you take the unit ball in L2 0 to T. You fix. So now what you do is actually don't go up to infinity. You fix it to 0 to T. You look at the unit ball in L2 0 to T, and give actually the weak star topology there, and that you take that, use that, and then now you see here there are F1, F2, etc. Isn't it? So now this B with the weak star topology, take the product topology there, and then use that topology here. One can show that it's actually going to be compact, metrizable, and in fact it will be polished. It will be a polished, complete separable, even compact. Yeah. So it is a nice space. So you can, but you need to give the weak star topology. But need lot of details there. So I'm not going to do it. Okay. So that's the idea here. I think I only have time to put the ideas. Okay. Is all right, isn't it? So what one going to do is actually the difficulty here is, this is difficult, but that can be handled using this. This comes with a martingale inequality, and the proof of this is not very, it's standard basically. So if you look at any book on stochastic calculus, you will find this techniques. And for this, either you can show that there is a minimizer here, and then take the minimizer, show tightness, take one limit point and pass to the limit. Or you look at delta optimal controls and pass to the limit. Okay, so, and that will tell you that for some V naught, X naught, minus alpha phi X naught will be less than or equal to 0, and hence the infimum over all V in V. And now, so that's the subsolution, super solution part of the viscosity solution. Here you have a less than or equal to inequality, because keep in mind that you need to actually take the minus everywhere. Okay, so it's actually the super solution part. Okay. Yeah, so any doubt, please ask me now.
The exit time estimate, that's not exponential for a diffusion.
No, it's with bounded coefficients.
Pardon?
Bounded coefficients here.
Yeah, so the best estimate available for diffusion with the bounded coefficients, isn't it? The stopping time is, I thought it's, you get an exponential estimate, no?
No, here you won't get. So it is easy to see. So what you do is actually look at norm of xt minus x naught whole power 4.
Yeah.
And then you have two terms. One is the bounded variation part, and second one is actually the martingale part.
Yeah.
So first part will be, and is will be less than or equal to some constant multiplied by modulus of integral 0 to t b of blah blah power 4. And then b is bounded. So there you will get a t power 4 there.
There are large deviation estimates which are.
But this is not large deviation, is it?
No, for diffusion, this is what the diffusion escaping tau ball, right?
Yeah, for a very small ball.
Yeah.
So I will be taking t to be less than or equal to 1.
Yeah.
So if it is deterministic, this estimate is obvious. Suppose sigma is 0.
That's a good.
Huh? Then is it obvious?
What's the question?
The question is that now this is take the stopping time.
Yeah.
Assume that my process is without linear process. Okay. Then it is a deterministic process. Okay. Then is this estimate is open. You can always define the infimum for which xt minus x naught is equal to epsilon. Everything is defined.
I think it should be, isn't it?
No, that's what I'm asking. So xt is the progressive expansion. X naught plus.
No, you just write down xt will be x naught plus integral 0 to t b.
The order of t again. The order of t is see the order of t square.
T squared is a worse, even worse estimate. I was asking
Yeah,
whether
this,
you have an
no,
exponential.
that will be for t less than or equal to, and this is that you are always get, isn't it? See,
Yeah, that's what. That's what very.
this is what you are looking at.
Right, exactly.
Now you just look at BT, isn't it?
That's what. Therefore, you get the order of t square is I don't see.
Oh, t square is
That's, when you use the fact that sigma is not equal to 0.
t power 4. I think there is.
Anyway, we can talk about.
Yeah, this. I think there is some. Yeah. Okay, so so this is the first one. So one can see that the value function is a viscosity solution. So now,
The same procedure works for the other integrity, right?
yeah, the same thing. So now what we'll have is second theorem. So if if you have two bounded continuous viscosity solutions to one, then they are identical. So here again, what I will do is I'll just tell you the main ideas. Okay, to do that, what I am going to use is I will be using the following Ishi's lemma. That will like. I'll just do only for the continuous functions. So if u comma v are in C of Rd and the function, okay, no need. So you take is an open set in Rd. And if psi has a local maximum, then there exists non-negative definite symmetric matrices such that and satisfies 1, 2, 3. So this will be crucially used. Okay, so the method is something like this. So what you do is actually, you want to show that they are same. So first we will show that u1 is less than or equal to u2, that's enough. If not, so there is an x naught which is in Rd such that u1 of x naught will be bigger than u2 of x naught. So now what you do is actually just define this, where c is some positive constant, and that we will decide later. Okay, so now you choose delta positive such that u1 of x minus u2 of x minus 2 delta psi of x, the supremum of this is positive. So this you can always do because of this. So choose delta small enough and let it be rho. So this you will be doing, and then so now note that so you fixed your delta, and now note that as the norm of x goes to infinity, this will go to minus infinity. So the is a maximum. So let x bar be the maximum. So that means let x bar belongs to Rd be such that is equal to rho and which is positive. Then what you will be doing is define for each lambda positive, you define it as minus delta y. This again, so when norm of x plus norm of y go to infinity, it will again go to minus infinity. So it has a maximum. So suppose x lambda, y lambda be the point of maximum. Maximum for psi lambda. So now what one need to do is actually need to observe the following thing. So one is actually this is bounded in lambda. So that x lambda, y lambda is bounded. And then second thing is actually, so it will be having a limit point. So any limit point will be of the form xx. That
Because x lambda minus psi lambda plus 0.
this you can avoid this. You can just remove this and only look at this. So you will get a bound. You can make you can choose an r positive so that this will be always less than or equal to r, which is independent of lambda. So that's it. Okay. Yes. Yeah. That is there. So the next thing is so take any limit point, and that limit point, any limit point should be of this form. That means, so whenever there is a limit point, it's something like a diagonal. That again follows from one again. Yeah, just you need to do something. What you need to do. So this is bounded. So take this guy to one side, and then so what you can show that this will be bounded. Once this is bounded, this will happen. The next thing is next thing is you take, so next thing is actually this, which is the most important. This goes to 0. So how do you see this? What you need to do is actually look at this. Look at psi lambda of, I will just keep this as an exercise. So this is the supremum, isn't it? X lambda, y lambda is the supremum. So this is always greater than or equal to psi lambda of, you take x lambda, and then write down the expression, and then what you will be seeing is actually this, x lambda, y lambda. Just expand this, and what you see is something of this kind, some y lambda minus u2. u1 will get cancelled, plus delta will come, minus, and use the continuity. So you will get this. So once you have all these things, is the time to apply the Ishi. So now what you do is, so you cannot apply Ishi for psi lambda directly. So what you do is actually you just write, you just define new functions, u, which is u1 plus delta psi, and then u bar, which is u2 minus delta psi. Then what you see is actually this psi lambda of xy, you can see it as y minus lambda by 2 mod x minus y the whole square. The last term will get cancelled. So now you are in the Ishi's framework. So what you get is, and then again you know that x lambda, y lambda is a maximum, so it's a local maximum. So apply the Ishi's lemma. So what you will get is actually there exists Q1 and Q2, which are in S of D, such that I will use it, I will remove it here. So what you have is lambda, and here what you have is but what is this? This will be what is your u? U is this, so it will be u1 of x lambda. See, this is a smooth function, so this will become plus delta d of psi at x lambda, and then second derivative. Similarly, so this will be this. Okay, so that means you are getting some elements in here, and then that is the right place to apply the viscosity solution. So what one get here is actually, so there exists Q1, Q2, etc. and with this property. So what was the property? With lambda, x lambda minus y lambda plus, not plus, minus derivative of psi at x lambda comma Q1 plus second derivative of psi at x lambda, which belongs to the semi-jet of u1 at x lambda. So now apply the fact that u1 is a viscosity solution, so you get one inequality, and then again now what I can remove? Ishi I will remove. And similarly, what you will, okay, so using that, then what you will get is actually alpha u1 of x lambda will be less than or equal to 0. B of, now you need all the terms, dot, what is it? Trace of, so I will just denote sigma transverse by A multiplied by Q1 minus this, and similarly use the second one, and for U2 what you will get is something like this, but this will become plus and similar term. So now what you will do is actually just subtract. So what you will get is u1 of x lambda minus u2 of y lambda, and what you can see is actually this is less than or equal to. So now we just see that so here there is a term like this, and then okay, this will be x lambda. So I'll just this is what will happen. Something like I'll just take write one term, and there will be, I'll not write every term. So lambda of x lambda minus. So finally you can you just use the triangular inequality, and then so that I can split everything and make into supremum, and then this. So what you will get is actually, you take actually the term here and the corresponding term here, what you will get is actually modulus of this of y lambda comma v multiplied by lambda mod x lambda minus y lambda. So this will be one term, and now what you see here is this is bounded, and then lambda, this will go to 0, so that term will go, and similarly this term will remain, but they are bounded, isn't it? So
That is square lambda into x lambda minus y lambda square go to 0.
which one?
There is a order of convergence is there.
Yeah, that's right. So what I'm missing here?
This nature of B must be used.
Okay, yeah, precisely. Yeah, yeah. What I will be using is actually I will be using the Lifschitz constant.
That's going to come.
That's what I should be doing. So this term, this will be x lambda, and that is easy. And then what one get is actually this term will be there, which does not have any x lambda minus, there is no lambda here, and this can be uniformly bounded because, yeah. And then what, and the other difficult term is actually going to be this. This, what one does is actually you are going to use actually the Ishi's, you will be using, that is gone.
Yeah, it is. You erased it.
Yeah. So what you have is actually this. This will be used. when you use this, this can be written, okay, that I will do. So this and some easy term, and then here what term you have is actually 1 by 2 trace of. So what you have? This will be a q1, and what was the next term? It will be minus of that, so it will be q2, isn't it? And then plus 1 by 2 delta will come out. Then what will? Huh?
That is not significant.
Yeah, that's not significant. There is some term in terms of d square psi x lambda and y lambda. And now this, what one does is this, yeah. No, this is not x. No, this is not correct. So what you will get is I won't write the other term. So this is x lambda is there, isn't it? So that's actually the thing. So it will be q1 minus a of y lambda of q2. Now this, now I will just take this term. This is done. So what you do is actually this, you can write it as trace of, look at this, sigma x lambda. I mean, what I meant is actually sigma of x lambda, sigma prime of x lambda, then sigma of x lambda, sigma prime of y lambda. Then you will be having, I think I want to check whether there is a minus there. So this will be y lambda, sigma prime of x lambda, and then the same, sigma prime of y lambda, then q1 0 minus q2. I think this is right. So that is the manipulation you need there. Yeah. No, yeah, that is right. So now what you do, use is actually you use this. Huh? Oh, this is q2. Now you use this. So replace your q1 and q2 with. So what will happen is actually this will be less than or equal to 3 lambda will come, and then it will be I1, I minus I minus I here. Now just multiply. What one going to get is, so this will become this. Now I don't need this. What one get is actually this 1 by some lambda and then 3 by 2 trace of sigma of x lambda now you use actually the Lifschitz property. So finally what one get is actually, and now using, so now use the Lifschitz continuity, and then what one get is, and then take to the limit. So what one get is actually this, and this will be, so what was our limit? This will be less than or equal to some constant we will get. No, there are some other terms here.
Delta is 0. I mean delta also go to 0, right? You are making delta also go to 0, right?
Yeah, no. Delta I am not making. Delta is fixed. So you get a constant because all the other things are bounded. And now what you do is actually, see that this constant is not going to depend upon actually psi, but what it will depend upon is actually only the gradient and the second order term. So now I will choose C in such a way that this will be less than or equal to some 2 delta psi of x tilde. And that gives a contradiction. So that's the proof. Huh? No, you take where is the psi tilde? Ah. No, it will contradict this. So now you pass, take x tilde here and let, and this will be positive because this is positive at x tilde. And so here, when you pass x delta, you replace this x and y with x tilde y tilde and pass, take lambda to infinity along that subsequence, you get actually a strict other way inequality. So now this argument is actually going to give you this. So that's the contradiction. So anyway, what I will do is actually I have my notes. I will just mail you tomorrow, and then so all the complete details are here. So now I think I have some 15 minutes. So this, so it's still not done. So what one need now to show that the value function is actually the unique viscosity solution, what you need is actually show that the value function is continuous. So once you have the continuity, then clearly it is bounded because of the form of the value function. So once it is continuous, then it is a unique viscosity solution. Okay. That's actually the next. Yeah, so to do that, first I will define the following. So what is alpha naught? It is the supremum over all x not equal to y, such that and comma v. So define this. Now I will state the theorem, and this will be finite. So use the Lifschitz continuity. So the theorem is the following. So if your alpha is greater than or equal to alpha naught, then the value function is Lifschitz continuous. And if alpha is less than alpha naught, then it is Holder continuous with the exponent alpha by alpha naught. Okay. So here again I will just sketch the ideas. So here, see, one point I should be telling is the following. So what is the value function? Value function is infimum over all v dot of this. So where v dot is running over all admissible controls, or in particular all the feedback controls. And now what? So feedback control, one know that it is of the form some f of t x of 0 to t. So take a feedback control, and then suppose x dot is a solution, then what one can do is actually this. So this is one solution for actually that equation. Then what you do is actually just look at the following control. So you have an x dot on some sitting on some probability space with a Brownian motion. So that is given to you now. So now what you will do is actually now you define your v tilde to be f of, so you call it x cap because that's given to you. Now look at this. Now look at this control. So this is prescribed. Is all right? See, because so corresponding to this there is a weak solution. That means there is a probability space omega fp with a Brownian motion and this process such that corresponding to this is actually going to be a solution. So now I am going to take this. On this probability space, I will define this control, which is prescribed. Same f. But now it is given to you. So I have a probability space with a Wiener process and this process. Now I will define this control. Now for this particular control, just look at what is the solution of this equation. This will have a strong solution, unique. So you use actually that because you are given that B and sigma are actually Lifschitz. So corresponding to that prescribed control V tilde, there is a unique solution, and what will be that? It is going to be this x cap, isn't it? So the bottom line is actually, if you are given feedback control, you can replace it with a prescribed control. So the value function is essentially what you can do is actually value function is nothing but taking the infimum over all prescribed controls. So that we will be using it here. So that's the main idea. So now once you have that, then things are easy. So you can restrict yourself to all the, so the value function you can actually treat it as actually the infimum over all. Which one? Yeah, it's a complete process, but for each t. Okay. So that is, so this infimum, now I am going to write the infimum over all prescribed controls. That is what I need. So now, so what will be this? So that is directly not possible. Okay, that's possible. So this will be less than or equal to supremum over all v dot, which are prescribed of, see here it is x. Now I will not put x here, I am going to put it inside, but I will tell what I am going to do. So and just tell me this is all right. So here xx denote the solution solution corresponding to V dot which is prescribed and initial condition x naught equal to x. Similarly, so xx is the solution with the prescribed control V dot starting at the point x, and similarly this. So now this will be less than or equal to the Lifschitz constant of R, and then what you will have divided by alpha, expected value of, and then there is a supremum. Should not be doing it. This. So now what is left is actually estimate the expected value of this. To estimate the expected value of this, we'll be using this. How much time I have? 5 minutes. Or yeah. Okay, so I'll just design it. So what I need it now is actually to estimate this. To estimate this, one will be using the Ito's formula for this. So use Ito's formula and write down this. So what one will get? So what we are going to do is actually apply Ito's formula for mod x square. So what we will get is mod x naught minus y naught, sorry, x minus y square plus integral 0 to t. So what one get is, that's the equation. So it is b of xxt xss ds minus derivative of this, that is 2 dot ds plus the second order term. So what will be that? That will be this. So that is precisely why I wrote that. So this will be 1 by 2 summation over I sigma ii what the condition precisely is actually whatever the term I am going to get to when I apply Ito's formula to mod x square, and then it is square, so there will be a 2 here, so that will go, and plus there is a 0 mean martingale time. I am not going to write that because anyway I am going to take the expectation, so it will become 0. 0 mean martingale, the term which contains the Wiener process. And now you take, okay, so here what one need to do is actually so this will be one need to divide and multiply by. Okay, so now you just see that what will happen when see now I need to use that mod x minus y square. So that another point here is actually then when x equal to 0 I have nothing, so this is not well defined. So what I can do is actually till the time this process reaches coincide, I am going to do it. So what I will, and so what will happen when they are, so this I can write it as, so this is same as the indicator if this all right, this is not equal to all right, isn't it? So this ds is same as this whole term multiplied by this. Otherwise it is 0 anyway, isn't it? So do it here, and now then you divide and multiply it by this term. So I will just take only one term. Other term is similar. And multiplied by this, I am just keep in mind that I am working on that event. And similarly this, and now, and similarly this term, and now replace that with alpha naught. So this will be less than or equal to plus integral 0 to t. Now just see that. See this term plus this divided by this whole multiplied by this is what we have, and whole term in the bracket is alpha naught. So this will be just alpha naught and ds multiplied by the indicator on this, and which is further less than or equal to this. So now, so this is what one get whole square. Now take expectation and apply ground wall. We will get this estimate. Now one need to use it here. Okay, so that now for this. So now combine all these estimates. What you will get is this will be less than or equal to that. So this will become independent of the choice of your control. So what one get is and some Lifschitz constant R. Go. Getting it to 2 or yeah. So because so that this will imply that, and
Not that way.
just see.
Here if I apply the holder inequality.
Yeah, not there. Yeah.
Minus 2 alpha t.
So this is
There
I will be taking it here. dt, and then what I will do? So this
Yeah, and apply the older.
dt. Correct, isn't it? So this, yeah, minus alpha naught t dt. Okay. Huh?
Now you must split the interval into 0 to gamma and gamma to infinity. You must
Yeah,
use
yeah,
the different
yeah.
depending on
I think
based on
I,
the
yeah.
order of the
Yeah, this is not the way to do it. I have done it correctly here.
So, what's the problem?
No, there will be a problem. So I need some t here. Otherwise, see for I will not be able to do for this. I need little bit more than that. Here, see if alpha naught is greater than or equal to alpha naught.
e to the power alpha naught t.
Yeah. See, when alpha naught is greater than alpha, this calculation is enough. There is no problem. But when I need this, so this will just be infinity. So I should not do that. So here, so I need to. So I should not be even doing it here. So what I need is fix for a t here, and then okay, I will be yeah. There was an r here. So first integral 0 to t. The other term is actually from t to infinity of e power minus alpha t r of xxt vt minus r of xyt vt, and then here just take the bound. So what you are going to get is actually just 2 norm of r infinity, and then from integral t to infinity e power minus alpha t dt. So this will be the term one is going to get, and so this term will be equal to 2 r naught, and what is this? So this is e power minus alpha t divided by alpha. So that term will come. So this will be t and plus alpha, and here again t and now. So this will be just integrate it. So now the point is, so this is true for every t. So now what you do, what one need to do is actually, so for alpha greater than alpha naught, one easily found that it is Lifschitz continuous. When alpha is less than or equal to 1, so what one need to do is actually look at this expression. So this gives you a function of in t, and this is true for every t. So what one need to do is actually take the infimum over t, and that infimum over t will give you the order continuity.
Equal both the terms.
What is that?
T says that both the terms are equal. That is how it is interpolation inequality.
Oh. Yeah, but the way I did is actually just I just calculated. Yeah.
Minimizer or
Just minimize and then find that t star and then plug in the t star, and then that will give you the, so that calculation I am leaving. So that is so this is, so the point is actually, so there are only 2 points here. One is actually how one replace the admissible control into feed precise controls. Once you are in the precise control, then you can use all this Lifschitz continuity of the coefficients. And then once you have the Lifschitz continuity, then do the calculation, and finally you are into the setup of ground wall. Use the ground wall, get this estimate, and then just the second part is actually this. So you get a function in t, and since it is true for every t, that's the improvement. Then take the infimum, and then that will give you the Holder estimate, Holder continuity. Okay. So these notes I will send you tomorrow, and then all the details are here. Okay. I think I will stop.
Let's thank Professor